Hello, and welcome to the Cartesian coordinate system, distance and circles. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. Applied calculus is what used to be called business calculus. It's calculus for those that are not in sciences or engineering. I'll be talking about the Cartesian coordinate system with a special focus on the distance formula and equations of circles. So the Cartesian coordinate system, first of all, that's a crazy name for it. It really is just, it's named after René Descartes, French mathematician. Long dead, so you can't even kill him for making you learn all of this stuff. But it's a great way of representing algebra visually. So this is algebraic geometry. So what we have is a number line. And then we have a number line that is horizontal and a number line that is vertical. And where they meet is the origin. This is the 0 on the horizontal number line and the 0 on the vertical number line. We call them the x-axis and the y-axis. Technically, they're the abscissa and the ordinate, but that's all right. X-axis, y-axis, that's just fine. We start at the origin. And on this Cartesian coordinate system, also known as a rectangular coordinate system, we can find any point P based on the x value, right, the distance away from the origin on the x, followed by the distance away from the origin on y. So it's like first name, last name. Or a street address, right? We have numbers followed by the name of the street. It's just a location finder for our Cartesian coordinate system. For example, here's our x-axis all labeled, and our y-axis all labeled. Notice the positive values go to the right, the negative numbers to the left, just like we had on our number lines. Similarly, positive values go up, negative values go down on our number line, same as before. So this point A has an x value of 2, so we've moved to the right 2 from the origin, to the right 2 and up 3. Whereas the point B, we've moved to the left 2, and to indicate left, we call that negative 2, comma 3. If I wanted to go left and down, they would both be negative. Go to the right and down, so x value is positive, y value is negative. We also have what are called quadrantal points. I had to think there for a minute. Quadrantal points are points that are on the axes. So here's a point F that is a 4, 0. It is 4 units to the right of the origin, but 0 means it has not gone up, nor has it gone down. It is on the x-axis at an x value of 4. Whereas this quadrantal point G, x value of 0 means we have not moved right, we have not moved left, we're right here on the y-axis, and we've gone down 5 units, so 0, negative 5. So why are they called quadrantal points? Well, this coordinate system is broken into 4 pieces, and with the 4 pieces we call them quadrants. So quad, right? Quad generally means 4. Think of it as the sun rising in the east. Sun rises in the east, quadrant 1. It sets in the west, quadrant 2, comes back around, quadrant 3, quadrant 4 to reset for the next day. I know the sun doesn't move, but that's our view of it as an Earth-centric people. So quadrant 1, quadrant 2, quadrant 3, quadrant 4 as we go around, and they're both x and y are positive in quadrant 1. X is negative and y is positive in quadrant 2. They're both negative in quadrant 3. This is not an emoji. And quadrant 4, the x value is positive and the y value is negative. So that's the Cartesian coordinate system. We'll be using that quite a bit. In fact, we use it to define our distance formula. So in our coordinate system, if I have 2 points, x1, y1, and a second point, x2, y2, what we're going to do is we're going to use the Pythagorean theorem. We can draw, right, from our first point, we can draw a horizontal line that comes out, and from the second point we could drop a vertical, and so we have a nice right angle here, right? A horizontal, something parallel to the x-axis, and a vertical parallel to the y-axis, guaranteed to be a right angle. A squared plus b squared equals c squared, and this c squared, this hypotenuse, is the distance that we're looking for. This is football analogy. You run 10 yards out and cut 5 yards over. What's the path of the football? All right, here we go. So the distance d between 2 points, point 1 is the x1, y1, and point 2 being x2, y2, in the plane, also known as the Cartesian coordinate system, is given by d, the distance, is the square root of the entire sum, x2 minus x1 all squared plus y2 minus y1 all squared. And that is the distance between the x's, right, also known as a squared in our Pythagorean theorem, plus the distance between the y's, y2 minus y1, square that. And normally that would give us distance squared, but we don't want distance squared, we want the distance, and that's why we took square root of both sides. This is a great formula for a note card. Reach for it when you're at a red light instead of your phone. People behind you will honk a lot less. So let's do some examples. We're going to find the distance between the given points. First example, points are 1, 0, and 4, 4. So x1, y1, x2, y2. So I'm going to take the difference in x's, 4 minus 1, and square it. Then the difference in y's, 4 minus 0, and square it. 4 minus 1 is 3. Still keep the squared. 4 minus 0 is 4. Keep the squared. 3 squared is 9. 4 squared is 16. Add inside the radical first. You don't want to take the square roots yet, right? Remember, the square root is a fancy exponent, and you can't take an exponent of a sum, so you have to simplify the sum first. 9 plus 16 is 25. Then we take the square root. The square root of 25 is 5. Let's do it again. 2 points, negative 2 comma 1 and 10 comma 6. I'll take the difference in the x values, 10 minus a negative 2, all squared, plus difference of the y's, 6 minus 1, all squared. 10 minus a negative 2, remember, subtracting a negative turns into addition. So 10 plus 2 is 12, still squared. 6 minus 1 is 5, still squared. 12 squared is 144, 5 squared is 25. We'll add these first to get 169. And then we'll take the square root as our last step, the square root of 169 being 13. And of course I gave you perfect examples instead of something really hard that has a radical in the answer. But the methods, the steps are still the same. Always subtract the x's, subtract the y's, square each of those results, add those two terms, and then find the square root of the result. We can use the distance formula also to find the coordinates of the points that are 5 units from the origin, and have an x-coordinate equal to 3. So let's break this down. From the origin tells us we're looking at the point 0, 0. That's where the x and the y-axis cross. The x-coordinate of 3 tells us we have a generic point 3, comma y. And the 5 units from indicates a distance, right? I want to find the points that are a distance away. So I'm going to use the distance formula. In this case, my distance is 5. The square root of, and I have my points here, I'm going to subtract the x values, 3 minus 0, all squared. I'm going to subtract the y values, y minus 0, all squared. And yeah, I can't really do that, but I can still call it y, so it's all good. 3 squared plus y squared. Now I can't combine the 9 and the y squared. They have no like terms. Remember, addition and subtraction, very, very important that they have sameness, and they're not like terms. So in order to find what our y value is, what I'm going to do is undo the radical, and the opposite operation of a square root is square. So what I'm going to do is I'm going to square both sides. I'm going to square the 5. I'm going to square the square root. Right, so as long as I do it to both sides, I keep everything balanced. 5 squared is 25. The square root squared just gives me the radicand. The radicand is the thing under the radical, 9 plus y squared. Now, I can solve for y squared. I'm going to subtract 25 from both sides, and 25 minus 9 is 16. I'm going to use the square root property, and the square root property tells me that a 16 equals y squared. Then plus or minus the square root of 16 is equal to y. We all know the square root of 16 is 4, so that tells us that y equals plus or minus 4. Once you think you're finished with a problem, always go back. Find the coordinates of the points. Oh, that's just some y values. The coordinates of the points are x coordinate 3, y coordinate negative 4, and x coordinate 3, y coordinate positive 4. So make sure you answer the question that is asked, not just complete the work necessary to get you there. Answer the question. Also using the distance formula, if we square both sides, square the radical, square the r, if our r was a distance, we would end up with x minus h all squared plus y minus k all squared equals r squared. And this is exactly the formula for the equation of a circle. So, if I have a circle, draw the circle first, and then I'll put the coordinate system on top of it. My center is the point hk. The radius, r, is the distance from the center to all the points that are equidistant. Alright, so a circle is defined to be the set of all points equidistant from a fixed center point. Alright, equidistant, distance formula totally makes sense. And we use the distance formula in a form that doesn't have radicals. So x minus h all squared plus y minus k all squared equals r squared, where my center is the point h comma k. Let's look at a couple of examples. Find an equation of the circle that satisfies the given conditions. If my radius is 3 and my center is at -2, -4, all I'm going to do from the previous slide, hit pause, go back if you need to, come back here. I'm going to do x minus -2, that's my h value, all squared, plus, a lot of people forget the plus, don't forget the plus, y minus a -4 all squared equals 3 squared, r squared. So I put everything in exactly as it says, x minus h, oh my h is -2, all squared, plus y minus k, oh my k is -4, close in parentheses, oh that's squared, equals r, oh r is 3, squared. And then I'm going to tidy it up. This, that's alright, but that's hard to read. If I subtract a negative, that's addition. So that's x plus 2 all squared. Much easier to read. Plus, instead of y minus a -4, let's call it what it is. It's y plus 4 all squared. 3 squared makes 9. And this is our final answer. It's a nice looking equation of a circle. But you don't have to know specifics. You can have general circles as well. Suppose the center was at -a comma a and has a radius of 2a. Don't get lost in the numbers. A circle is x minus h, the x value of my center, so that's -a, all squared, plus y minus k, and in this case the y coordinate of my center is a, squared equals radius 2a, all squared. And notice I use parentheses here, whereas I didn't with the 3. A single value squared, pretty straightforward. If I didn't have the parentheses, you would just think this was 2a squared. Make sure the 2a is all being squared. Subtracting a negative, that's x plus a all squared, plus y minus a all squared equals 2a times 2a is 4a squared. Equations for circles using center and radius. That's it for Cartesian coordinate systems, specifically looking at distance and circles. Thanks for listening.